by managing expectations. First thing is, this is not my title. This is a title that I was given. It was actually for a workshop that took place in November, so I was assigned this workshop. It was also a 20-minute talk, so I added a few extra slides. But really, the biggest caveat here is that this was a meeting where there were many, many things discussed. There was, and overall, the message of this workshop was really how complete the SUSY searches really are. Okay, and so it was not an easy thing to be told, okay, now come up with the things that you're not looking for. Okay, so since the talk was just 20 minutes, I just wanted to as a sort of a pre-introduction, I just wanted to show just a few of those, some highlight graphs from the rest of the conference, so you can get an idea what the rest of the conference was like. And we can talk about those. I'm not totally prepared. Whoops. Okay, so yeah, so this is, I guess, this is the disclaimer slide that I had at the conference. And as you can see, a lot of the things that you would think about, at least in the early days of SUSY searches, people worried about, wow, will SUSY searches see this, will they see that? A lot of these things have really been addressed. And so what I'm trying to do here is to be very modest and just discuss a few areas that were not discussed so much at the conference. Okay, but let me just say something about the existing SUSY searches that we did hear about. Some of these you may know about, some of them you may not. So one point is that a natural loophole to worry about in supersymmetry searches, they generally rely on missing energy, but if the second to lightest and the lightest particle, or in general the spectra of all the superpartners, is very compressed, then there's very little missing energy. Okay, but now all the standard searches here, so these are all sort of jets plus missing energy searches, they're all pushing very close to these degenerate lines, where this one not so much, but they're definitely doing this. And also, even if you're not very close to this line, depending on where you are, this is the mass of sort of the mother particle, this is the mass of the LSP. In different regions of this, there are different cuts, for example, that are optimal, and these things are now optimized essentially independently in regions in this entire plane. So in any given region in this plane, not just near here where they drew the limit plot for a standard SUSY, these searches have been optimized sort of bin by bin. Okay, and they're like I said, they're pushing towards this degenerate limit. So that's something that's going on. The other thing is that actual searches for R parity violation are coming up. These searches right here are resonance searches. So I wasn't planning on going into any detail on any of these unless somebody stops me. This is just a very general sort of overview. But these top two right here are resonance searches that come from CMS for various R parity violating couplings. And you can see that you're getting limits around here, 700, here 900, 800 or 900 GeV masses for the initiating particles. So in the general sense is that R parity violation isn't the giant loophole that it used to be. Here are very different searches right here that have to do with leptonic R parity violation, and here one is just using the multi-lepton searches to just put bounds on these scenarios right here. Okay, and again, you're talking about 1 TeV type scale masses for the initiating particles. Okay, so these bounds are very strong. Also,
I didn't pull your screen down far enough. I'm losing some of it.
Yeah, so let's see if I can get this. All right, I think it works.
To do it.
How do I do? There we go. Okay, sorry about that. Okay, and so another sort of area where specific searches are being done are cases where only the particles that are really necessary for naturalness are light. So you may have a much sparser SUSY spectrum. They're lower masses, lower production rates, lower energies, or lower missing energies, for example, overall. And in these cases, there are also these various dashed lines are various places where there are near degeneracies that suppress the missing energy. And again, these searches are pushing towards these regions by doing optimized searches. They're being done here. Here's for stop-initiated things, for Marino-initiated things. All of this is being done, okay? And of course, no sign of a signal in anything, right?
Sorry, Marcus?
I'd be giving a very different talk.
Could you go back to the RPV one?
Yes, sure.
So this is the bound for the X. You produce a heavy X and X decaying through jets.
Yeah, this one, that's right. That's what these top two are. That's right. And so this one, I have to see what are the differences here. I have to remember. So these are different R-parity violating couplings. So this one I think has third generation stuff, and this is light flavor jets. I think that's the difference.
So they're one like including a B-tagging or something?
Yeah, I think this one here is the let's see, this I believe is the heavy flavor case. So this one probably uses some B-tagging, so which is probably why it's a little better than this. This is just light jets.
I see.
And I think similarly here, the difference here is this is heavier generations. This probably has taus. Does that make sense? Yeah, maybe. I'm not sure. I'm guessing this is taus and this is non-taus. I'd have to look back at the original slides.
Okay. So this is assuming we produce an X and X decay into a jet and some scalar and then scalar decay into two jets. If I want to apply this to the
These up here, I believe
Yeah,
so.
yeah.
Yeah, that's
Okay,
right.
I see.
I think that's right. Okay. All right. And you know, if you, this is actually, I put that slide in there on the conference. There's actually, the talks in the conference were very good. So if you want more detail on these, the talks were very nice at the conference, and the slides are all there, of course. Okay. And also, electroweakinos, it's another case where you know, they're pushing very hard, and you can see in the most optimistic scenarios, you can actually get up to you know, 600 or 700 GeV the chargino mass. Of course, again, there are many of these sort of degenerate regions here, depending on the model. And again, these are very specifically being pushed towards, so they're optimized searches in these, basically in these whole planes here. Okay. So overall, you know, the message is it's not so easy to come up with things that you'd say, well, you know, when are the experimentalists doing this search and that search? It's not so easy to come up with things because it's really, really impressive. Both at Atlas and CMS, the coverage looks very, very good. Okay. Okay, so that was just some slides that I added just to put things in context. So now I'm going to sort of segue into the actual talk that I gave at the conference. And like I said, that was sort of, I think it was a 20-minute talk, so I'm going to try to talk slowly, and if there aren't a lot of questions, we'll finish early. Okay, and I've never had anybody complain. That was a great talk, it was just too short. I've never heard that. So I'm going to apologize for that. Okay, so the big picture is, of course, that, you know, this is a graphic from Chip Brock at Snowmass, which I like very much, is from now on, for the foreseeable future, we're going to be seeing everything, particle physics, through Higgs glasses, right? We've discovered the Higgs, and it completely changes the way that we look at everything. So what we found is 125, maybe 26 GeV Higgs, and the couplings, as well as we're able to measure them right now, look standard model-like. And so what does this tell us? Okay, so now it really has, one big message I want to convey is that this really has reduced the realm of the space of possibilities, right? There's this picture that somehow particle theorists have thousands of models and they're all different. So first of all, most of those models are not really different, and second of all, most of them are now dead. So we have supersymmetry, that's one thing that's still alive. We have a composite Higgs that's still alive, and the only other possibility is that we don't know what we're doing, okay? And I really think that's that really is pretty much the only three viable possibilities now. Okay.
No extra dimensions?
Extra dimensions are this.
Okay.
Any viable theory of extra dimensions has got to have a composite Higgs in it, or it's in this category. Okay. So I mean, the extra dimensions have lots of other stuff in them, but as far as what they do for the Higgs, they look, from the bottom up, they look identical. They're just a version of a composite Higgs model.
And there's still no other fundamental Higgs theories that don't have SUSY in them?
I don't know of any. I really don't know of anything that makes sense. I mean, I can say that one thing that is in this category is just lots and lots and lots of fine-tuning. Okay, I put that in the category of we don't know what we're doing. You may put that in a separate category if you want. But then this really is a complete list. I'm serious about this. You know, I'm not, okay? So I think that's good. I mean, this is really a measure of how much we've learned. It's really incredible. So of course, I'm going to be focusing on supersymmetry here in this talk because it was a workshop on supersymmetry. Okay. So this is part of I'm trying to set the stage for what I see to be the big picture. And so again, what have we learned? Well, there's actually been a tension in particle physics really since the 1980s. Okay, as soon as the Standard Model was written down and people started looking at its problems, they found that as soon as you try to improve the Standard Model, you also make it worse. Okay, if you solve problems in the Standard Model, then you create new problems. And actually, there's really only one problem in the Standard Model. There's only one problem, which is, so the Standard Model is actually the perfect, absolutely perfect effective field theory. An effective theory is one where you say what the particle content is, you say what the symmetry is, and you write down everything that's allowed. Okay? And the Standard Model is the most perfect example that we have of an effective theory if only one parameter is tuned. It has one defect, which is encoded in one parameter, which is precisely the effective mass, okay, that we get by integrating out all the crap, heavy stuff, so that we have this effective field theory on the Standard Model. This one parameter its value is unnatural. That's the one problem with the Standard Model. And the fact that there's one problem means, and so every time since the 1980s, literally, since the very beginning of particle physics beyond the Standard Model, every time you tried to fix this problem, you started creating new problems. Flavor-changing neutral currents, okay? Then precision electroweak, okay? And now also the fact that we haven't seen any additional new physics at the LHC. And in every case, in order to explain why we didn't see anything, particle physicists like me invented theories, okay, where it was natural that this thing was small, and yet somehow you managed to avoid all the other difficulties. But to avoid the other difficulties, you had to construct things just so. So the way I visualize this is that what we were doing was building ever more elaborate houses of cards, okay, where this is stable, this is not, right? But this doesn't really look like it would occur naturally in nature. This looks man-made, right? So that's kind of that's sort of the analogy that I think about. And so, you know, a lot of times with naturalness and simplicity, we use those things interchangeably. Here I'm using them in a very precise sense. Naturalness means there's no tuning of parameters. Like here, to make this thing stand up, you have to adjust the angle just so in an artificial way. But simplicity is the minimality of structure and assumptions, right? There's only one assumption here. There's a lot of more structure and things going into this, okay? And that is really, I think, where we are. You know, we've been getting more and more this way since the 1980s, and now we're there. This is it. Okay. So now this introduction is hopefully makes you a little bit uncomfortable. It was certainly intended to make you a little bit uncomfortable. Okay. And so I want to tell you a story that's supposed to make you happier. This makes me happier, so I'm going to share it with you. Okay. It's a true story. In the early 1990s. There were limits on the people were trying to look for deviations from the blackbody spectrum in the cosmic microwave background. Okay, that was, of course, was understood very well. This is a fundamental parameter in cosmology. This would tell you about dark matter, about structure formation in the universe, and so on. And the quadrupole is the lowest moment. It's the easiest thing to measure. It's the discovery mode. It's the place where you would expect to discover deviations from the blackbody spectrum, okay? But in the 1990s, there were limits on the CMB quadrupole. It was not observed, and they were pushing the limits of cold dark matter cosmology, okay? So this looked to be a kind of a crisis in cosmology. Now, you don't know about this because, of course, what happened is along came COBE, okay? The COBE experiment very beautifully measured not just the quadrupole, but a bunch of other higher multipole moments, okay? But COBE was at a higher sensitivity than where you expected to do the discovery. So what is the explanation for this this temporary crisis that there was in cosmology. What about the quadrupole? Well, if you look at a more modern graph, of course now we don't just have a few multipoles, we have many, many multipoles, and this is not even the best one. So where's the quadrupole? Look, the quadrupole's right there. So blow it up, okay? So this band is the expected range based on the fact that the quadrupole is one number. We only have one universe, right? So this number is drawn from a distribution, which the theory predicts. And so this is called cosmic variance. It's just the fact that there's one measurement. And roughly this is about 1% too small. You can see all the other ones are beautifully, within the sort of statistical fluctuations. They lie exactly where the theory predicts. But this one, which is the discovery mode, one thing happened to be smaller, and it corresponds to sort of 1% tuning. So, would you have told cosmologists in the 1990s that they should have given up on searching because, look, they found bounds on the quadrupole which were already much smaller than the expected amount? It's a good thing, right? They didn't quit, okay? And so, this is a perfect analogy for what may very well be going on in the standard model, is that it may be that things are just, there's a 1% sort of accident in a single parameter, namely the Higgs mass, and that would explain why we haven't seen anything beyond the standard model.
Marcus?
Yeah.
When you say 1% tuning, is that same as saying one? Is that the p-value?
Yeah, I mean it really is. So there really is a well-defined distribution, and it's even Gaussian, okay? Because the primordial density fluctuations are Gaussian, and so the fluctuations here are Gaussian, and the theory tells you what this band is, and so there's a really well-defined p-value there.
So
that's right.
The pink band is not uncertainty or systematic uncertainty? Or?
No, it really is the variance. I believe it's the cosmic variance here. Okay, so the claim is if you do this, if you calculate this, the probability of this happening, it's about 1%.
The closest you can get is still very far away, given that error bar system. So guys should be looking at the bottom tip of that pink thing versus the data point.
That's right, that's right. So this is, I don't know if this is 2 sigma or what. I just copied this slide from somebody. So
See it over and over again.
Yeah, right. But so anyway, I think this is my favorite analogy. There are many other analogies, examples you can think of fine-tuning in nature. This is the one that I think is the closest analog to what we actually have. And the message is clear. It's saying don't give up, okay, just because things are not looking, aren't coming in right where you expected them. Okay, so then what do we have to talk about? We can talk about supersymmetry where there's just some tuning. There's just some 1% accident like this. What I said about the standard model is true in supersymmetry. There's just one parameter that needs an accident. And even if you don't like it and you can't explain it, it might be that way. And if there was this accident, I should have said explicitly, it automatically means in the context of SUSY, for example, that all the rest of the superpartner spectrum is heavy. That's just a natural consequence of, it's a direct consequence of tuning this one parameter and not tuning anything else. Okay, so we can look at that. We can ask, we can have a sort of a 1% tune supersymmetry, or we can try to say, well, no, SUSY is actually more natural than that. It's just hidden in some clever way. Those seem to be the two main alternatives.
Marcus, what did you mean by rest?
Rest? I'm not sure.
You said all the rest is at some high mass.
Okay,
So
what I mean is that
so all the superpartners, or there's some superpartner left down in a moiety.
Yeah, so I'm imagining that there's some theory of supersymmetry breaking that predicts the particle masses, the superpartner masses. And for generic choices of parameter space, actually, what tends to happen in supersymmetric models is that the stop and the Higgs have roughly the same mass. But now, there's just some unexplained accident. You've got many parameters and you just, by accident, tune one. What happens is that everything moves around a little bit, but because you've made this one special accident, the Higgs goes down. So this is 120, that's the generic thing. Of course, you could tune more things down, but each additional thing you tune down is an additional tuning. So if you're going by the accident theory, you would just think that everything was just quite a bit heavier. That's the generic expectation. And actually, if you ask me what I think is the most likely, I would say that's probably the most likely thing to me. But you can make your own judgment. But it's possible that you can have a more natural spectrum, and it could be sort of, more devious in the way it hides itself from experiments. So those would seem to be the two possibilities that you want to take a close look at. Okay. And the thing that I'm going to spend most of my talking about is because this is, even though I think this is probably the most likely thing, I think that this is incredibly important to test, and this is where we need to be more clever, okay? Because here, the superpartner spectrum just gets heavier and heavier, we just have to keep pushing harder and harder, and there's not very much for theorists to say, but there's a lot more for somebody like me to say in natural SUSY, okay? And so the two things that I want to talk about are beyond the MSSM Higgs, so the MSSM is already an extension of the standard model, the minimal supersymmetric standard model, but beyond that, beyond even that in the Higgs sector, and then I want to talk about displaced vertices, and these are possibilities that arise naturally in natural SUSY. That's what I'm going to talk about for the rest of the talk. But first, I want to make clear that I'm not dissing tuned SUSY, right? And so I really think the best way of explaining why that's compelling is just, from the 12th century, 11th century, right? Occam's razor says entities must not be multiplied beyond necessity, right? Occam's razor just says you want the simplest theory, and like I said, if you want to start having things more natural, you really have to give up simplicity. And so I think it's very arguable that the MSSM with one tuning is the simplest explanation of particle physics data, okay? And the implication of this are, and this sounds like a joke, but it isn't, SUSY is most likely just around the corner. And that's a time-independent statement, right? If you raise the bounds a little bit, it'll still be true, okay, for quite a while. And I don't apologize for it, that's true, right? Okay, so the message is just keep pushing for the standard SUSY signals, okay? And certainly that will be done, and I hope that people still continue to be excited about it, okay? It's very, very important, okay? But natural supersymmetry, which may be have a little bit more of the conspiratorial air about it, I think is still crucial to test. Before we just say to ourselves, okay, well, nature's unnatural, we should look under every bush to make sure that we're not missing something, right? And so the basic requirements for SUSY naturalness are that the Higgsino masses, the mu parameter, be less than about 200, the stop be less than about 500, the gluino about 1.5 TeV. And these are very rough, these are naturalness estimate, they're squishy estimates, so these are just a guide, okay? And so you can see what this motivates. This motivates electroweak Eno searches for these guys, stop searches for these guys, and cascades of gluinos into stops for these guys. Those are the three basic kinds of searches that you want to make sure that you're doing if you believe in a scenario like this. But there's something that, and this is something, as I said, that's very well covered in existing searches, which is the only reason I'm not talking about it. But another thing that is not appreciated quite so much, and which I'm going to talk about, is that natural SUSY also requires the Higgs sector to be beyond the MSSM. Okay, not be the standard MSSM Higgs sector. So I'm going to explain why that is. Okay, so even though the MSSM is a 2 Higgs doublet model, the important features for what I'm going to be talking about you can describe in just a 1 Higgs doublet model. So we just have a quadratic and a quartic term. Okay, and the VEV fixes some combination of the parameters. Okay, and so since we know what V is, and now we know what the Higgs mass, we know what lambda is. Okay, and the fact that the Higgs is too small in supersymmetry can be traced to the fact that lambda is too small. Okay, so it's not really the Higgs mass problem is really a problem with the quartic coupling, a dimensionless quartic coupling. So if you want to fix this problem without using the conventional tuning of supersymmetry, you need additional contributions to the quartic, okay? And beyond those in the MSSM, because in the MSSM, we need to tune the stop loops. So we can either have the NMSSM, where we can have tree-level contributions to this from extra singlets. Another possibility is non-decoupling D terms. You can have additional gauge interactions which give additional contributions to this quartic. Okay, but actually, it's up till recently the only thing that was considered was additional contribution to this quartic, but there's actually another possibility, and that's something that I've been working on, is that you could have additional Higgses that also break electroweak symmetry, and that electroweak symmetry breaking can give you additional contributions to this potential that already violate electroweak symmetry in the potential before you do the minimization. And this turns out to be a viable thing. We call it induced electroweak symmetry breaking because it actually arises from a tadpole. So in those models, MH squared is positive, and you get a tadpole from some new sources of electroweak symmetry breaking, and it doesn't even matter how small the quartic is. Okay, so that's another class of models, and sort of in the sort of block diagram language that we model builders love so much, the way it looks is this: is we have the ordinary MSSM with the ordinary MSSM Higgses. We have some new Higgses, okay, some singlets and some doublets that couple to the Higgs. Okay, and this sector breaks electroweak symmetry along with this one, but only these H's have Yukawa couplings. Okay, so this is another possibility. And the important thing for experimentalists, phenomenologists, the take-home message of this is that, again, this is roughly, I think, a pretty exhaustive list of what actually makes sense. It's not as completely as clean as the previous thing, but these are really, I think, the models that really make sense. 2 out of these 3 right here definitely require that there be additional Higgs bosons which strongly mix with the observed 125 GeV state. And so they directly motivate searches for additional Higgs bosons that have significant mixing to the 126 GeV state. And beyond the MSSM part of this that's important is that they really can have, in the MSSM, the amount of mixing you can have with the additional Higgs bosons to the light Higgs that's been observed is very limited by the structure of the MSSM. Here there are new possibilities. And so I'm going to give some examples of this. Now, whenever you expand the Higgs sector, you get a ton of new parameters, right? Even in a general 2 Higgs doublet model, you have, I don't know, 10 parameters or something like that, okay? But that shouldn't deter you if you're an experimentalist, because any given signal that you're interested in is completely described by a simplified model with a few parameters. So we should just do those searches and worry about it later if we find anything, okay? If we find something, then we'll worry about what bigger model it's part of. And the new feature in these models compared to the MSSM is that these heavy Higgs fields can be far from the decoupling limit. Mostly in the MSSM, generally, the heavy Higgs bosons are actually in a decoupling limit, which means that you can choose a basis where their contribution to electroweak symmetry breaking is very small. And that means that they essentially, in the mass basis, if you look at the mass basis, the fields that have the heavy mass have very small VEBs, and that basically means they largely decouple from vector bosons and also from the light Higgses, and that limits the kinds of things, ways that you can see them. Okay, and so here's an example of something which now I believe now searches are just coming out for this kind of mode. But this is these graphs right here are from a study at Snowmass that shows the promise of this mode. So this is A going to ZH. So A is a heavy pseudoscalar, and ZH going to leptons and B's or taus for the Higgs. Okay. And so what's plotted here is the parameter space here in this model. Here on the vertical axis is 10 beta. Okay, so there's a fixed value of MA, which is 300 GeV in this plot. Here's 10 beta, and here's cosine beta minus alpha. Now the relevance of this parameter is that when this is 0, you're in the decoupling limit. Okay, and these blue bands right here, the dark blue bands, are for, this is for type 1, type 2 Higgs doublet model. Let's look at type 2, for example. That's the one that's the most SUSY-like. This outer band here are what current Higgs coupling measurements are telling you. So the fact that the Higgs couplings are close to the standard model is forcing you to live inside this outer blue band. Okay? The inner blue band is what you're going to get with 3 inverse attobars of LHC data. So the high luminosity LHC will improve things a little bit, but not very much. Okay. Now these yellow contours are discovery contours for this mode. Okay. And what you can see is that in the absolute decoupling limit, the direct discovery craps out also. but it reaches in much, much closer to this decoupling limit right here, okay? Of course, but these are of course complementary because I chose, this was for 300 GeV. If you choose a larger value of MA, these yellow things go away completely, right? Because you just don't make these things. So the message is that if you want to study the Higgs, it's basically equally important to do direct searches as to do Higgs coupling measurements. They're very, very complementary, okay? And this is the same sort of plot for the type 1 case, okay? And I'm not going to go through it, but there's a similar story for example, capital H goes to ZZ. There's a very, very similar story where, again, you can see that the direct searches reach in much closer to this decoupling limit, the standard model-like limit. And these are, like I said, these are discovery contours, but again, only if the heavy Higgses are sufficiently light, of course. Okay? And yeah, there are other examples that one can study. Okay, and so some of which I'm actually looking at with collaborators.
Well, these are being done.
All of these?
Yeah.
So ZZH?
I don't know about ZZH.
Because that's the one. The other ones I know. The other ones I know. But this is the one that we are starting to look at. This doesn't seem to be a standard one.
Huh.
So I mean.
So you'd look for ZZ in leptons plus 2
Yeah, I mean, the first thing we're doing is just looking at the multi-lepton searches and just see how well you do. So, yeah. But yeah, I think that that's right.
The CMS multi-lepton result on the A to ZH and H to HH was just approved.
H to HH.
And I think
Yeah.
it'll be shown at ASPEN next week.
Yeah, okay, good. Yeah, so I think that that's right. I think it's not that experimentalists are and also for none of these things I should also just say to add to the caveat. I'm not trying to say that any of these things are a shock to experimentalists either. I mean, I wasn't able to come up with something that nobody had thought of, is really well motivated, and you can see it. I'm sorry, I wasn't able to do that. Okay, but these are just things that I just think should get a little more emphasis or a little more press maybe than they do. Okay, but yeah, I wish I had something totally exotic. Okay, so now I want to just say a few things about our parity violation, and again, this is just this is not necessarily totally new things, but anyway, so for example, baryon number violating our parity violation is often considered precisely because it's supposed to be a good way to hide natural SUSY. Okay, but what was is it actually been known for quite a while, but was recently re-emphasized in this paper, which I think is very nice, is that cosmology actually puts extremely strong constraints on this, which are very, very general and very hard to get around. Okay, and the basic point is that UDD destroys the baryon asymmetry in the early universe. Okay, down to very, very low scales, not just below the masses of the quarks, as you might think, but far, far lower. And so it actually, if you have this thing, if you have this UDD operator, in a very, very generally, you actually require both low-scale baryogenesis, and this operator has to be small enough so that you actually get displaced vertices at colliders. Okay, and so this is actually shown here, because this is in the plane of Swart mass and this lambda coupling. This is basically the NLSP mass. Okay, and here you can see what. Here you can see that you need, for example, in these shaded regions here, you need a baryogenesis scale below 50 GeV. You need to generate the baryon asymmetry below 50 GeV. Otherwise, this operator would have wiped out any baryon asymmetry you generated, no matter where you generated it. And then superimposed on this are the decay lengths of the NLSP. Okay, and when you put this together, you find that it's very, very hard to avoid. You simply cannot avoid having displaced vertices. Okay, and I don't know. I don't see anything wrong with this analysis. I don't see any simple way out.
So this is in low energy. That means even if you have left homogeneity, somehow give you the asymmetry.
It doesn't
In the
matter.
end, it's still asymmetry.
Yeah, because this is just wiping it out. And so as long as this is in equilibrium, it doesn't matter how you generate the asymmetry.
Right.
So they did a detailed analysis of, and so this basic point that UDD efficiently eliminates the baryon asymmetry seems to be known in the literature, but it seems to have been forgotten. I don't know. I didn't know about it until I saw this paper. I've yet to talk to somebody who told me, said, yeah, we know that. I know that since 1995 or something like that. So, but it seems to be true. So I think this is something to keep in mind if you're thinking, you know. And and just in general, I would say, even apart from this specific thing, it's very well motivated because these are parity violating couplings violate all sorts of symmetry. It's a very natural possibility that they're small, okay? And that can naturally lead to displaced decays of the NLSP, okay? And there are many, many possibilities you can have here. So, for example, in this kind of case right here, where you have a baryon number violating RPV, which is the case that I just talked about, you would get a displaced. Well, why don't I have a displaced track here? I know I should have a track here. I don't know why. Okay. Well, anyway, this thing. I think I may have gotten my graphs and my pictures messed up. If this thing was neutral, which it's not in this diagram, you could just get something like this, and the decay, if this thing decays inside your detector, you could just have an appearance of a jet like this.
The pattern has to be neutral.
Yeah. See, I think I said here neutralino, so I think that's right. This is supposed to be. Oh no, this is just virtual. I'm sorry. This is just the neutralino decay. This is right. The neutralino is just this guy right here. Yeah, it's your displaced vertex, and this is just some virtual. It's got stars. Yeah. Makes sense, right? Okay, so this is just your decay. It goes through virtual stops, or virtual whatever your lightest squark is. Okay. So and it goes to many, many jets, possibly leptons. So you would get nothing going into a displaced vertex like this. It's also possible that the NLSP is a chargino, then there's actually a simpler decay, then you could get an exploding track, right? You get a track out to this, and so on.
So there's no missing energy in the final state.
That's right, if you count all this energy here,
Yeah.
then you won't have any missing energy.
Depending on what your algorithm does with it.
Exactly. So of course, what you really would want is to find this separately and somehow add this up separately from that.
Except that you have a few neutrinos lying around.
That's right. In some cases, you have some neutrinos, so you actually, sorry, that's right. So in some cases, you do have missing energy. In this case, you wouldn't.
And the lifetimes could be basically anything.
Yeah.
So the heavy, stable charge particle switches would pick up the long-lived ones.
Yeah. Yeah. I mean, if
Oh,
you
wait,
look
no,
back,
not in that case. In the chargino case.
right, in this case right here, if it's very long-lived, you would just have a standard missing energy signal, right? Because it just escapes the detector.
But it'd be very low cross-section, because it's weak.
Well, I'm assuming this is really at the bottom of some cascade, for
Okay.
example. So I've drawn here, this yellow part is supposed to be the sort of some, cartoon of a hadronic SUSY. It's sort of the underlying SUSY event.
Yeah.
But it's very interesting, of course, right? There's a Nobel Prize here as well as here, right? So,
But now we can get it.
yes, okay. And another situation so the message is that our parity violation gives you a strong motivation for these displaced vertices. Another motivation for these displaced vertices actually comes from dark matter. Okay, so dark matter is actually physics beyond the standard model that we know exists. Okay, it definitely requires physics beyond the standard model. And what we're really interested in is not only can we perhaps detect it in the cosmos, but can we actually learn its identity by studying it colliders? And of course, there's a beautiful scenario for this. This is SUSY WIMP, and this is Mom and Apple Pie. I have nothing bad to say about SUSY WIMPs. They're great. Okay. But since we haven't seen any signals in direct detection and collider searches, it's certainly is telling us that we need to be looking at other mechanisms beyond WIMPs and to ask ourselves if there are other new signals that might be important in those cases. Okay? And one, I think, very natural set of possibilities, this is sort of on the menu of theories, something that I think is pretty appetizing, is to imagine that we have dark matter, but it lives in some hidden sector, and it only couples to the standard model, has no standard model gauge interactions, no strong interactions with the standard model. And the leading interaction is some operator singlet in the standard model times some singlet operator in the hidden sector. And the parameter, this can be a very naturally small coupling because this might be, for example, a higher dimension operator. So this can be very small, and still the dark matter can be happy in this hidden sector and have much weaker interactions with us than a WIMP. Okay? So and in SUSY, it's very natural that the LSP could just be in the hidden sector. That's why it's stable. It's the LSP. It happens to be in the hidden sector. Okay? And so then an important concept in this kind of model is the lightest ordinary supersymmetric particle. It's the lightest SUSY particle in the visible sector. And the reason that that's important is because no matter how small this is, if this guy, the LSP in this sector will naturally decay into the LSP in this sector right here. Okay? And this decay can naturally be long-lived because this operator can be naturally small. And so there are a number of examples of this kind of model in the literature. Historically, the first one that was considered is a super WIMP, which is basically a gravitino. Okay? But the example they considered was a gravitino, but it can be more general. And the idea is that the LOSP, the lightest ordinary supersymmetric particle, is so long-lived that it does all the things that dark matter does. It freezes out, it decouples, it's there in the universe for a long time, and then suddenly, oops, it decays. Okay, much, much later, after it's done its thing of freezing out. And then basically what happens is you dilute the energy density of dark matter by the ratio of these guys, but otherwise you have a perfectly good, you know, if there was a WIMP miracle before, multiplying it by order 1 number is still a miracle. Okay, so this motivates sort of weak scale stuff in the hidden sector. So the X could be a gravitino, but it could be something else as well. Okay. Another possibility that I think is very interesting is freezing dark matter. And here the idea is that the hidden sector, which has the dark matter, is never in equilibrium. Okay, it's never in equilibrium. And because of this little epsilonic interaction, we're always bleeding in a little bit of stuff into the hidden sector. Even though it's never in equilibrium, there's still, you know, it's like a little air leak or something, right? You're always leaking stuff into the hidden sector. And you can calculate the relic abundance in that case just as well as you can in any other situation. But the dark matter X is never in equilibrium. And then what you actually find is that for the, let me put in the parameters here, okay, that if you have sort of the smallest mass you can have for the dark matter, which this is set by cosmology, by structure formation basically, and the LOSP is about 100 GeV, you automatically get displaced decays. So this scenario works precisely when this coupling is weak enough that you have displaced decays. Okay. So that's something that's interesting about this scenario. Okay. And yeah, so this again motivates very highly displaced decays for the lightest ordinary supersymmetric particle. And the final example is something that I worked on, asymmetric dark matter. The idea is that you have an operator that has a charge asymmetry, for example, baryon number, coupling to an operator that has a charge asymmetry in the hidden sector, and you transfer the baryon asymmetry to a dark matter asymmetry. So a B minus L asymmetry in the visible sector is transferred to a dark matter asymmetry in the hidden sector. And then when you freeze out, you get a natural connection between the dark matter density and the baryon number density. So rather than being a freeze out type thing, the dark matter density is naturally tied to the baryon number density. So this can explain why these numbers are only about one order of magnitude apart. Okay. And in this case right here, so one thing is that this squiggly can actually be turned into an equals. You can actually do a real calculation, and it actually makes a definite prediction for what the dark matter mass is once you fix the charges that are here. So this is the minimal set of charges right here. And it's generally light. It's about 14 GeV. Okay. And so this prediction is valid for as long as this mass, this parameter here that couples these things is sufficiently heavy, okay? And that also means that, again, the loss, the lightest ordinary supersymmetric particle here will decay to these guys, and this coupling being big means, again, the decay is naturally displaced. And so you can see for sort of reasonable parameters here, even m as low as a TeV, in this particular case right here, you can easily get centimeter type couplings. And there's a whole zoo of different possibilities, that some of which we look at in our paper. Okay. Notice this is very uncertain. Notice this -9 power. So it's very, very sensitive to the details of the spectrum that you can very easily get displaced vertices. So anyway, so again, the kind of thing that you can get out of this is you would pair produce the lightest ordinary supersymmetric particle, which say in this case is neutral, and then it decays, so you would sort of pair produce these things. So I want to point out that not only is this a good discovery mode, but this is really awesome because if you see an event like this, you have the possibility of fully reconstructing the underlying SUSY event, if you like, right? Because now you actually know something about the kinematics of these guys. In the best possible case, this particle would actually be charged, and then you would actually know everything. You would literally know everything, okay? Supersymmetry can be completely reconstructed, right? But even if it's neutral, you can actually use the vertex position and the timing, and you can still get it, right? Okay. Because even without a direct energy measurement, you can't. The difference is that in this case, you can't measure the momentum of this, right? But you can still get the constraints of this. So this is, of course, yeah, wildly optimistic. Okay, and so so the dark matter mass leaves this detector, right? Remember that's actually the reason why this is non-trivial. Is that remember that in this scenario there is missing energy that's always leaving these displaced vertices. Okay, but you really do, even in this case right here where it's neutral, you have enough information if you know these vertices and the timing. You have enough information to fully reconstruct the event. It turns out.
I've got displaced jets limits.
Right.
Have we published it?
I think the displaced jet. I think it's a CMS search on displaced jets, which I believe is out.
Yeah.
That's right, and that got a lot of rave reviews at this conference. A lot of theorists are very happy that that's there. So I mean, I know these things are hard, but now that we didn't see anything, maybe people can be interested more in the little bit wilder and crazier things that we haven't been looking for as carefully. Okay, so that's it. So the most important thing really is not the holes. The really important thing is, most important thing is that to an amazing extent the searches really look very complete and very impressive, and the experimentalists have done an amazing job. And as my overall theory perspective is that we should take very seriously both tuned and natural versions of SUSY. I think we should be just humble and say they're both plausible and very important to test. And you can have your own favorite if you like, but I think we need to test them both no matter what. And a little attempt to give a little push to, in this talk, to BMSSM Higgs and displaced vertices. Okay, thank you.
So maybe I missed it. Did you mention R hadrons? Are those part of these models?
Yeah, I mean, I think R hadrons are important. I mean, I didn't. I could have found a slide. Actually, the searches for those. Again, it's one of the cases where it's not easy to come up with ways they could be improved. They look for these searches are being done now, and they really are sensitive to lifetimes. From years to I don't know. That's nanoseconds or something. Yeah, literally years. Mm-hmm. They literally have, for example, these searches have, they have the entire beam history, for the last whatever months for every little microseconds. And they actually, for every lifetime, they just compute a probability. There's just a likelihood that you're going to see an event at that time for these long-lived cases. you know, and so again, it's a
This
case
is when
where
they stop. And
I didn't talk about it only because it's already done so incredibly well, it's really hard to see how we could improve the
So
searches.
the one aspect that is very different, well, there are, I guess, lots of them, but I guess it's only the R hadrons that can charge exchange as they go through the detector,
Yeah,
and
that's right.
a neutral one becomes charged and
So you get dashed line.
dash
tags.
line, dash Morse code.
Yeah, so those I'm not, you know, those, I'm not sure exactly to what extent there are searches out for those. I believe there are some out, but I don't know the details.
Even
of
worse,
those.
during the gaps, the particle goes straight, doesn't curve.
Yeah.
Those
I
are
mean,
hard to
I
find.
think you know, that a lot of, some of these searches, you know, if you don't see anything, you don't see anything, right? But then, if you want to know what you've excluded, you know, you have to know, for example, how often do these guys dash, you know, how quickly do they stop if you're doing the long-lived searches, okay? But my impression is that it's generally believed that the very long-lived case is the most efficient way to search for R hadrons. Sufficiently many of them stop, and you really you're sensitive to a very, very long range of lifetimes, and then you're really, really sure that you know what you're doing, because you're not subject to uncertainties on, you know, how often do they dash.
Right.
You don't really know that. You know, there's some model you could use, but, you know. So my impression is that the long-lived searches are really the thing that really bites into that.
So I think you mentioned at one point that you find the most likely scenario is MSSM plus a 1% accident. But so why? So implicit is that the standard model as it is has to be tuned much higher than the MSSM, or
No, the standard model is just automatically the effective theory that you get when you do that, and so I mean the connection between these two things is that if the standard model is the low energy theory, okay, if there's some limit where, you know, everything that's not in the standard model starts in some heavier mass, okay, then we can say very, very cleanly that there's only one parameter that's needed to get, that you know has to be fine-tuned from a bottom-up point of view. Now, from a top-down point of view, in SUSY, we also know that 1 is the minimum number of parameters you can tune to get that. So, of course, tuning is supposed to be, you can have even more tuning, but, you know, the basic point is that it seems that to explain what we see, you only need one tuning, and that automatically means that the low-energy theory is the standard model. So, and like I said, that's really been true since like 1980s. As soon as people started thinking about Technicolor and supersymmetry, they immediately ran into the problem that these generically mess up flavor. Okay, and then this was seen as an opportunity because then you could find fixes for this, and that meant that your new physics had to have special structure, which is very interesting. So if you discovered it, it would be great. But then you kept having to have more and more special structure just to explain that you didn't see anything. So that's where we are now. And so I think, yeah, the simplest thing is there's just one accident, and we have to live with it.
okay, no more questions, and we should thank our speaker.